Exercise 1.1 of Class 12 NCERT book. Questions on reflexive, symmetric, transitive, and equivalence relations. Determine whether the following relation is reflexive, symmetric, and transitive. Relation R in the set A 1, 2, 3, 4, etc. till 14 is defined as R is equal to ordered pair x, y such that 3x minus y is equal to 0. As we know, any relation in set A is a subset of all ordered pairs, set of all ordered pairs from A to A, which is called Cartesian product or cross product of A and A. Now, which are the subsets, which are the elements that can be included in this subset? Only those ordered pairs which satisfy this condition. Here we go. Ordered pair 1, 3, 2, 6, 3, 9 and 4, 12. These are the only 4 ordered pairs which will satisfy this condition. Let's check. Say 2, 6. Place x as 2, y as 6. X as 2, y as 6. 3 2s are 6, minus 6 is equal to 0 is true. Similarly, these 4 ordered pairs will satisfy this condition given to us. Hence, this relation will include only 4 ordered pairs which I am going to list down. Now, this is called a relation written in the roster form. Just by listing down the ordered pairs which satisfy the given condition in the relation. This way of expressing the relation is called set builder form. Now, the same relation is depicted through an arrow diagram also. Now, we need to check whether the relation is reflexive. What is reflexive relation? A relation in set A is called reflexive relation if ordered pairs of the form A, A belong to the relation for every element A of the set A. That is, elements of the form AA means both coordinates are same. X and Y same. X, X. Let's see. 1, 1, 2, 2, 3, 3, 4, 4, etc. are the elements that should be present in this set to call it a reflexive relation. Will they belong? Let's go by checking one element. 2, 2. Check 2 here, 2 here. X is 2, Y is 2. 3 into 2, 6 minus 2. It is not equal to 0. Hence, 2, 2 does not belong to the given relation. That is why we did not include 2, 2 pair here in this relation. 2, 2 does not belong to relation. It goes as a counter example. An example that counters the definition. An example that goes against the definition. Which proves that the elements of the form A, A do not belong to the relation. Hence, R is not a reflexive relation. Let's see whether it is symmetric relation. What is symmetric relation? A relation in set A is called symmetric relation if the pairs of the form A, B, if it is present in the relation, that should imply that the pair B, A also should belong to the relation. For every A and B, whenever there is a pair of the form A, B is there, the pair of the form B, A, the reverse one, should also be there. Let's go checking. I'm taking an example 2, 6. 2, 6 does belong to the relation. Yes, that is why we had picked it up. But can we find a pair in it 6, 2? No. 2, 6 is there in the relation, but 6, 2 is not found among them. 6, 2. When x is 6, y is 2. When x is 6, y is 2, the equation is not going through. So, this numerical example goes against this definition. So, we say the relation is not a symmetric relation. Let's see whether it is a transitive relation now. Transitivity. A relation in set A is called a transitive relation if you have ordered pairs of the form ABBC in the relation, then it should imply that the ordered pair of the form AC also belong to the relation. What is special with these two pairs? ABBC. This B is kept common in both ABBC. Let's go and check. Do we have such pairs here? Yes. 1339. 1339. So we say now 1339 belong to the relation. Yes, they are found in the relation. But 1339 are there. Can we have a 19 also? The elements AC? 19. No. 19 is not found in it. Why? Because x equal to 1 and y equal to 9 will not satisfy this. That's why the pair 19 was not taken. So we mentioned that though we could have 1339 elements in the relation, the element 19 is absent. It goes against the definition of transitivity, which acts as a counterexample now. So we conclude this relation is not a transitive relation also. Now, a relation which is reflexive, symmetric and transitive is called an equivalence relation. This is not an equivalence relation. Determine whether the following relation is reflexive, symmetric and transitive. Relation R in the set n of natural numbers defined as R is equal to ordered pair x, y such that y is equal to x plus 5. This time the set given to us is set of natural numbers 1, 2, 3, 4 etc. till infinity, all integers, all positive integers. That's what set of natural numbers. Now the relation is defined from set n to set n. The ordered pairs that we will include in this relation should satisfy this condition. Ordered pair x, y may be included in the subset in the relation if the second element y is equal to the first element plus 5. Let's see what are the ordered pairs which can be included in this relation. Ordered pair 1, 6. Check whether 1, 6 can be included. X equal to 1, y equal to 6. Y equal to 6, x equal to 1. 1 plus 5 is 6, 6 is equal to 6 is true. So 1, 6 pair satisfies the equation, the given condition. Hence we can include 1, 6 in this relation. Similarly, 2, 7, 3, 8, 4, 9, 5, 10, etc. All those pairs which satisfy this condition will be included in the relation. Let us list them down in the roster form. All the pairs are just simply listed down in the roster form. 1, 6, 2, 7, 3, 8, 4, 9, 5, 10, etc. Infinite number of pairs are there. So the relation is now written in the roster form, listing down the pairs. The relation was given in the set builder form, where the condition is mentioned for the pair to include in the relation. And by this time we have drawn an arrow diagram also of the given relation, depicting the respective ordered pairs which can be included in the relation. Now we are asked to check whether it is reflexive. Reflexive relation. A relation in set A is called reflexive relation if ordered pairs of the form A, A are found in the relation for every element of the set A, which means they should have been ordered pairs of 1, 1, 2, 2, 3, 3, etc., which are the form AA. That means both coordinates same. Is it possible? Can x, x be included in the relation? Check. X plus 5 cannot be x. X comma x will not satisfy this equation. That is why any of those elements are not taken in this relation. So how do we express it? We show one example. Here 2 comma 2 is not included in the relation. As we know, 2 plus 5 is not equal to 2. So this example acts as a counter example. An example which goes against the definition of reflexivity. So we say this relation is not a reflexive relation. See whether the relation is now symmetric. What is symmetric relation? A relation in set A is called symmetric relation if A comma B pair included in the relation implies B comma A also included in the relation. Let's go checking. I'm taking an ordered pair, say 2 comma 7, as in the form A comma B. Yes, 2 7 was picked up for the subset, which satisfied the condition. But can we have a 7 comma 2 also? No. 7 comma 2 not, of course, it written here. But let's check whether 7 comma 2 can be included in the relation. X7 and Y2. 7 comma 2. How is it possible? 7 plus 5 cannot be equal to 2. So 7 comma 5 will 7 comma 2 will never be in this relation. That you highlight here. Though we could take an element 2 comma 7 in the relation, we cannot find a 7 comma 2 in the relation, which goes as a counter example, an example that goes against the definition. So we conclude that the relation is not a symmetric relation. Now we will see whether it is a transitive relation. A relation in set A is called transitive relation if the ordered pairs A, B and BC belong to R implies ordered pair AC also belong to R. Let's take if there are some elements of this form AB, BC. What is special with AB, BC? AB, BC means here these two elements B are kept same in both ordered pairs. Let's see, do we have some pairs of that kind in the relation? 1, 6, 6, 11. Yes, B is kept common. B is kept same, 6. But these two elements, do they really belong to the relation? Yes, I can see 1, 6 here. But 6, 11 I did not write here. Let's see, 6, 11 as such does belong to the relation. X is equal to 6 and Y equal to 11. I will check here. X equal to 6 and Y equal to 11. X equal to 6 gives me 6 plus 5 is equal to 11 here, and Y is equal to 11 here means it's correct. Yes. So both of these pairs do belong to the relation. But to call it a transitive relation, whenever there are elements of the form AB, BC, there should be element of the form AC also present. That is, we have to check whether 111 can also be included in this relation. 111 in place of A and C, 111. Can we have 111 pair in the relation? Of course, I have not written them. Let's go and check. 111, X1 and Y11. X1 and Y11. Oh, 1 plus 5 is 6 only. How is it 11? So, 111 cannot be included in the relation. Now, this numerical example now goes against this definition of transitivity. We did take a BBC pair, but we could not find a pair AC in the relation. So, we conclude this relation is not transitive. A relation R in set A, which is reflexive, symmetric and transitive, is called equivalence relation. Is it an equivalence relation? No, no, no. It's not reflexive. How can you call it equivalence relation? So this given relation is not an equivalence relation. Determine whether the following relation is reflexive, symmetric, and transitive. Relation R in the set Z of integers defined as R is equal to set of all ordered pairs x, y such that x minus y is an integer. This time we are given the set Z, set of all integers, and the relation is defined with this condition. Those ordered pairs whose elements x and y, the difference is an integer. In fact, any two integers x and y will satisfy this condition. So all ordered pairs made out of integers can be included in this subset. All ordered pairs using integers, which is in fact Z cross Z, the Cartesian product of Z. The complete Z cross Z itself is the relation this time. Now let's see whether this relation is reflexive. What is reflexive relation? A relation in a set A is called reflexive relation if ordered pairs of the form A, belong to R for every A of the set A. Here, let's check whether the ordered pairs of the form A, can belong to this relation. Place A, or x, whichever it is. The condition is only this much. Both elements should be same. So x, will it belong to the relation? We can check. Place x in place of y also. X minus x is equal to 0, which is an integer. That is, x minus x is 0, which is an integer for all x. Hence, x, pair will belong to the relation. That means the relation is reflexive relation. See whether it is symmetric relation now. The definition of symmetric relation. A relation in set A is called a symmetric relation if A, B pair belong to R implies B, A also belong to R. Let's cross-check. Take an element of the form x, y belong to R. If x, y belong to R, x minus y must be an integer. That is a condition x and y should satisfy to belong to R. So it implies x minus y is an integer, which can be written as x minus y is equal to m for some integer. Now let's see what about y minus x. If x minus y is m, y minus x is minus m. Of course, if m is an integer, minus m is also an integer. So the pair y, x will surely belong to R. Now it's being logically proved whenever the pair x, y is there in the relation, y, x can also be found in the relation, which is what should be satisfied by the relation to call it symmetric relation. So this given example relation is a symmetric relation. Now, is it transitive relation? To call a relation transitive, we have to check that whenever a pair of two pairs of the form A, B and B, C are there in the relation, we should be able to find the pair AC also in the relation. Let's go by taking two elements, two pairs of this pattern. Let x, y and yx belong to the relation. X, y and yx, something special. The element y is kept common in both of them. Here it's the second element, here it is the first element. If these two pairs are there to be transitive, for this relation to be transitive, we should be able to get an element xz in the relation. Let's see. We have already taken this kind of two pairs. Let them be there in the relation we have assumed, which implies x minus y is an integer and y minus z is an integer. That is what these numbers should satisfy to belong to this relation according to the given condition in the relation. If x minus y is m and y minus z is n for some integers m and n, We will try to eliminate the middle element y now. By adding these two equations, we get LHS x minus z, RHS m plus n. So we get x minus z is equal to m plus n, which is also an integer. Since m and n are integers, m plus n will be an integer. That means this present statement says x minus z is an integer, which implies x comma z will be an element of the relation. Hence, here we logically prove that whenever the elements of the form A, B, B, C are present in the relation, we are able to find the element of the form AC also in the relation. Whenever x, y and y, z belong to relation, the element x, z will also belong to relation. Hence, this relation is satisfying the definition transitivity. So, this relation is a transitive relation. A relation R in a set A is reflexive, symmetric and transitive is called an equivalence relation. This example given to us is reflexive relation, is symmetric relation, is transitive relation. Hence, this relation is an equivalence relation.